podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk all about modeling projectile motion. And I've mentioned to my class, Mr. Sadler, that this is probably one of the more difficult topics we're going to talk about this year.
Even though they do this all the time in every video game, cat physics or Angry Birds, you see it all the time. You can actually see the line in Angry Birds.
I know. It's just difficult to combine the X motion with the Y motion and add in gravity and the fact that time is passing.
Right.
There's just so much going on that it took human beings a long time to figure this out. It was actually Galileo, of course, that figured out projectile motion. He didn't understand it, but he figured it out, and he wrote a book that the Roman Empire used so that they could launch things at people and make their war efforts more successful.
Right. So we talked about that man has known for a long time that 45 degrees gets it the farthest.
Yeah. And so what we know about projectile motion is that it's parabolic. And I think in pre-calculus they actually talk about this. They model it, and they talk about the fact that it's an upside-down parabola, and they do a whole y equals function, and they say, well, it's equal to, the a term times x squared plus bx plus c, something like that. And as long as that's negative, then you get something like that. So there is some crossover between math and physics, of course, but I don't really want to focus on the math side of this. But I want you to keep a close eye on this equation because this is going to show up again. Actually, we've already seen it, but it is going to show up again. So you mentioned something about 45 degrees. What's special about the 45-degree launch angle?
So even ancient shooting the catapults at the castle, they knew that if I shot it at 45 degrees, or later on if I shot a cannon at 45 degrees, I could get maximum range.
Yeah, 45-degree launch angle, stuff goes far.
I thought it was funny. I had a student say to me today, yeah, but in Angry Birds it doesn't tell you what the launch angle is. But I remember the old games that they did actually tell you the launch angle.
Right. And the reason why it goes far is because if we were to analyze a right triangle, and this truly were a 45-degree angle, what we would determine is that the opposite side and the adjacent side are equal to each other.
Right.
So, you work this out. The tangent, I remember this from my trig class here at BBCHS, the tangent of 45 degrees is 1 because the opposite over the adjacent are identical values. They have to be equal. So there's a crooked equal sign. But so that's why it goes the farthest, is because it's maximizing both the horizontal initial velocity and the vertical initial velocity, right? If you go less than 45 degrees, so less than 45 degrees, it's going to take, how would we describe this? A flatter trajectory. So anything less than that, we're going to have an initial velocity horizontally that's bigger,
right,
but we're going to have an initial vertical velocity that's smaller. So if we were to call this VI at this launch angle theta less than, I can do math, less than 45 degrees. Okay, what happens here is Vxi, the initial x velocity, obviously the arrow's longer, it gets bigger, and the initial vertical velocity, the arrow is shorter, so it gets smaller.
Right.
So it's covering more horizontal space,
but it's in
equal
the
time,
air less time.
But it's, so delta t flight goes down.
Right.
And that's important.
So obviously you should be able to figure out if I'm a long jumper, if I can get in the air higher, I'm going to go farther.
Well,
generally.
And that's the point of diminishing returns, though. I mean, yeah, we don't want to launch at 15 degrees.
Right.
Ideally, we want to launch at
45.
I want to hit a baseball for a home run at 45 degrees.
Right.
If I'm a field goal kicker, 45 degrees. You're going for distance, Okay, this is your magic number.
Right. And then when we go for a higher launch angle,
Right.
you go over that.
We need theta to be bigger than 45 degrees. So this is going to be, it's going to have a higher arc, or higher arching
Right.
trajectory. And so once again, I draw, that's a straight line, I draw my initial velocity, and of course what happens here is I have a lower initial speed,
Right.
and the x, that's gone down, shorter arrow. I have a higher initial vertical velocity. And so as a result, its delta t flight does what? It increases, it goes up.
Mm-hmm.
And so it's in the air longer. So one nice thing that happens, if I can pull this off, okay, is that at 45 degrees we get maximum. At, say, 30 degrees, we don't go as far.
Mm-hmm.
But if we go 60 degrees and start from the same spot, something really weird happens. It's going to land
In the same
in
place.
the same spot. So a 30-degree launch angle, 30-degree range, is going to be equal to a 60-degree range. In geometry, we call 30 plus 60, we call it complementary
Right.
angles, right?
Mm-hmm.
The same would be true if we went 15-degree range with 75-degree range.
Right.
So it'd be even flatter still. It'd get to here, it'd go way up. But there it is. So bear with my pictures. They're not perfect, but your book has a nice diagram of this on page 189. This would be true of an 89-degree range versus a 1-degree range. Now, that seems silly, but in fact, it does work. And obviously, the complement of 45 is 45.
45, right.
And so they're going to have the same flight path.
Right.
It's just not as obvious. So that's all very interesting. I suppose the last thing I want to get into just briefly here is I've been drawing all these right triangles. So if this is the initial velocity, it's got an x and a y component because it's a vector. And I've been pretending that the math of this is not important, or it's not important to discuss right away. But if I wanted to solve for VI and I knew the components, I would do some right triangle trig, some
Right.
Pythagorean theorem. Well, I can do that. I can use my knowledge, and I can do better than VYI. I can say VYI, because this is the opposite side of the angle, then it's the hypotenuse times the sine of the angle. Since this is the adjacent side of the angle here, I can say it's the hypotenuse times the cosine of the angle. And it's going to give me values, and then I can check, of course, with Pythagoras. We haven't spent a lot of time with Pythagoras yet, but that guy was a genius.
Mm-hmm.
He figured out all of this triangle stuff. He was able to develop several proofs to his theorem in his lifetime. And he's the guy responsible for the diatonic musical scale. He realized that the musical notes that sounded good and pleasant to the human ear, there was a relationship between them mathematically. And that if you play some notes together, they sound really good, and if you play other notes together, they sound awful. He figured all that out with a harp and measuring lengths of string and doing stuff like that without computers and all of the wonders that we have today. So this launch angle thing, this initial speed thing, we discussed this in the investigation for 4. We've discussed it for the investigation in 5. And of course, the reason why an object just doesn't go up, up, and away, and it's really important to mention this, is
Gravity.
gravity. Okay? Gravity changes the motion of all projectiles.
Well, just one motion, though, right?
Right. And that's a good point to make. Gravity changes the y motion of all projectiles. It does, of course, it doesn't act horizontally. It doesn't act on it and change how far it's going to travel in the x direction. That's a very good point to make.
Correct.
I believe that covers the basics of this. We're going to, of course, do an AP Plus podcast on the technicalities of the math.
And I think this really leads to that chapter challenge too.
It does. If you're going to do shoot the grade, sections 4 and 5 are you got to be all over it
Right.
if you're going to get the 100% on the performance.
Got to know where it's going to be when.
That's correct.
Okay.
I believe that covers it. So signing off, this is Mr. White.
And Mr. Sadler.